The fifth question here says, three infinitely long charged sheets are placed as shown in the figure. The electric field at point P is going to be. Now, there are three infinite charged sheets here, and we need to find the electric field at point P due to the influence of all those three sheets. The first thing to remember here is that for an infinitely long sheet of charge with uniform surface charge density sigma, the electric field at any point at a separation r from it will be given by E is equal to sigma by 2 epsilon naught, and that is the magnitude of electric field. And if this charge distribution is positive, the electric field intensity vector will be directed away from the sheet, and if the charge is negative on this sheet, the electric field will be directed towards it. So these are things to remember here. Now, to find the net electric field at point P, E vector will be equal to E1 vector plus E2 vector plus E3 vector. That is according to superposition principle. We have three thin sheets here. We should find the electric field at point P due to each sheet and then do the vector sum to get the net electric field at point P. Now, we'll take each individual electric field here in separate and study that. The sheets here, I'll number them as 1, 2, and 3. So E1 vector will be the electric field at point P due to the first sheet here, sheet 1 here, and that will have a value that is equal to sigma by 2 epsilon naught, because the surface charge density of this sheet is sigma, and you know the formula already. And the direction of that electric field will be directed away from the sheet. So it will be downwards. This axis here is the z-axis. So upwards, you'll have k cap direction, and downwards, you'll have minus k cap direction. So this direction here of E1 vector, the electric field at point P due to the first sheet, will be downwards. So I'll have minus k cap to specify the direction of E1 vector. E2 vector, that is the electric field at point P due to the second infinite sheet, will be directed downwards. And that is because it's a negatively charged sheet and the electric field will be towards the sheet in that case at point P. So here is the direction of E2 vector, and that again is minus k cap. And the value of E2 vector, the magnitude, will be equal to 2 sigma by 2 epsilon naught, because the surface charge density of the second sheet is 2 sigma in magnitude. So you have 2 sigma by 2 epsilon naught as the magnitude of electric field at point P due to the second sheet. Now, E3 vector, that is the electric field at point P due to the third sheet, will also be directed downwards. And that is because E3, or the sheet 3, is also negatively charged, and the electric field E3 will be towards that sheet. So this is your E3 vector. Now, the direction is minus k cap downwards here, and the value will be sigma by 2 epsilon naught. And that is because the surface charge density of the third sheet is simply sigma in value. Now, then I can say that E vector will finally be equal to minus sigma by 2 epsilon naught k cap plus minus 2 sigma by 2 epsilon naught k cap plus minus sigma by 2 epsilon naught k cap. Now, if I take the vector sum here, I'll have minus sigma by 2 epsilon naught taken out in common, and then there'll be a k cap, and in the brackets I'll have 1 here, here I'll have plus 2, here I'll have plus 1 again, and that is minus 4 sigma by 2 epsilon naught k cap. When I cancel off 2 from both numerator and the denominator, the final answer would then be minus 2 sigma by epsilon naught k cap. Now, the option that matches with our solution will be option B, which says The correct answer is minus 2 sigma by epsilon naught k cap. And that is how we solve it. It is simply based on superposition principle and the electric field due to an infinitely long charged sheet.